So, last time we see how we can navigate through the universe and how we can make a map out of a seamlessly endless universe. Now, it wasn't exactly endless, but with scales and floats like very small numbers, then you can pretty much do an endless world around it. Now, for this part, we will actually see some more examples, not more examples, we will see some examples for steering AI and a spaceship the AI. And this is not going to be a pathfinding AI, but it's more going to be like an obstacle avoidance solution. Now, keep in mind, there are a lot of stuff you can do, and everybody has a different way to doing it. So I'm just going to show you one thing of what you can do. Other people actually have a star pathfinding implement on their projects, but this is a little much too much of an overkill, because you have to make a grid of a 3D space, and there are a lot. So think of it like having a nav mesh that goes in 3D. So anyway, I'm not going to stick too much on that. You can Google for a star pathfinding in 3D. We will probably do a video about pathfinding in the future. Okay, but I prefer to keep things simple, so that it's easy to follow around. So the first thing I'm going to do is duplicate my spaceship with all the collisions, and I'm actually going to parent all the other stuff I have over here. I will parent it under a new game object, and I'm going to close this. I'm also going to create a new skybox material, just so that we see what is happening. Okay, we don't need pretty stuff over here right now, and I'm going to close not this, yes, I'm going to close the copy direction on the game objects we have over here, that we had copying direction from the collisions game object, and I'm going to come over here. Now this is going to be a solution for every spaceship, okay, not necessarily for our own and the enemy's spaceships. It will work for everybody. Now, there are two ways of doing this. I'm going to close the user input, since we want to make an AI. The don't destroy is not actually needed, but let's just keep it. Now, one way we can do AI for this is to simply make another script similar to the user input, and similar to how we did in the third-person shooter third-person shooter series, where we have our basic controls over here, our basic movement control script, and the user input or the AI input is handled by a different script. Now, for a spaceship, and the spaceship that works in zero gravity and that works a lot with forces and the way we are moving this, we can make another script like this. But since, as you can see, there are a lot of values, and all these values will actually need to be tinkered down and bring them up into shape for making for every different spaceship we have, and it's not that much reliable, because we are moving a lot because we have given a lot of freedom to our players, and all the stuff will need to be adjusted for AIs. I have made a script for this based on around some other stuff I've seen, but it's actually too much of an encumbrance to make something like that. So let's just see how we can do it the easy way. Now, most games you will see, they might have an AI that controls the spacecraft the same way the spacecraft is controlled when the player plays it, but for most cases that's not really the case. Okay, for example, Star Citizen is more of a multiplayer game, so in a multiplayer you don't pass the physics through the engine, you learn the position of the enemies around, especially if they have a server, if it's not locally hosted, the multiplayer match, then all the movement of the enemies and stuff like that will be calculated through the server, and they will pass the position of where the enemies are through the connection. So it's not saying go with this, you have a rigid body. It's not saying, the network is not saying that add this force to that game object. Now I'm going to make some obstacles for us to avoid. So as I was saying, in the multiplayer you simply take the position of one unit and lerp it to the other, so you pass the position and the rotation through the network. Now I'm going to make the target over here just so that we know where we are going, and I'm going to change this to something red, and I'm going to make it sure that is in front of our obstacle. So okay, we have our gunship over here. Now we're going to need a rigid body. Okay, this is the same as the previous one. You can change the angular drag if you want. We will see how it works. Okay, we don't have any gravity, and now let's add a new component. Let me just add it over here, and I'm going to say Spaceship AI. I'm going to open it. I'll drop it in my Spaceship, and I'm going to open it in Visual Studio so that we can run it. Now this is going to be more of the avoidance part for waypoints and stuff like that. We will see if we have time. I will make it I will try and fit them in this video. Now first off, we will need the namespace of systems.collections.generic, and let's just add the system.link as well. Now of course we need to have a target. We need a vector3 for our acceleration. We need a vector3 for the velocity. We want to have a public float which we will say is the maximum speed. I'll give it I'll initialize it with 5, and I'm going to have another one which is store maximum speed. This is more of the current speed, not exactly the maximum speed, but we will say if we do changes to this, it will change it to all it will change the speed for all our objects. So we need a reference to a rigid body. let's add a new one, a target speed. We need, let's add it over here. We need to store the target, have a variable so we can store the target. Let's just add this also here. We need a boolean that informs us that we have saved the position. We need a boolean that it will say we need to override, we have override the previous target, and we need a list, and I'm going to add it beneath my rigid body. And for this list we're going to say this is going to be a vector3 list. I'm going to name it escape directions, and this will be a new list of vector3. Okay, so the start is going to be simple, and for the start we know we want to store the maximum speed. It will be the maximum speed. The target speed for now, it will be the stored maximum speed, and of course the rigid body will be get component rigid body. Now let's delete that. I think we know what update does. So actually we're not even going to use update, we're going to use fixed update. But before we go into writing stuff inside fixed update, let's create our helper functions first. And the first helper function will be actually a vector3, and we will call this move towards target, and this we will pass a vector3 of our target. Now this is going to be pretty simple. We need a check for the distance, and we want the distance minus the transform dot position. Now this give us the direction towards our target. Now if distance dot the magnitude, if we are close to our target, now I'm putting 25 over here, but you will have to make sure that you use numbers appropriate for your own spaceships. Okay. And the values I've used, I know the dimensions of my spaceship, so you'll be better off making all these public. Floats like this, make them public and change them from the inspector accordingly. And so if we are too close to our target, then what we need to do is pass the normalized the direction. The distance over here is also the direction, okay? But since we are close to the target, we need to stop, and in order to stop we need to pass the direction multiplied by minus the maximum speed. Okay, so it will actually make it either stop or brake accordingly. Now of course, since we are using physics, higher values mean a lot of more time for all this stuff to work. And if we are on the else statement, so if we are not close, then what we need to do is pass the direction, the direction multiplied by the maximum speed. So let's see that in action. But first off, let's see inside our fixed update. We want to do debug draw line, and we want to draw a line from the position, from our position to the target dot position. Let's save that. And now, so this will make a line so that we know where the target is and where we need to go. Now we want to make a new vector3, and I'm going to call this vector3 forces. And for this one, I'm going to say move towards target dot position. So our acceleration is the forces, and we're putting it in this in the acceleration variable, because if you want to add more stuff, you can add them over here. Okay, if you want to add more vectors, you can simply add them over here, just in case, because some people do avoidance by using physics. So one other way to do it is do a raycast, do few raycasts, and if you hit to the right, add to the direction and the rigid body forces, so that it will switch to the right. But anyway, don't confuse yourself with all that. So our velocity now will be plus equals, we will multiply this by 2 and multiply by the acceleration and time dot delta time. Now of course this will have to work with acceleration. If you don't want to work with acceleration, remove the time dot delta time, so it will automatically clamp to that position. So after that, we need to make sure that if the magnitude of our velocity is greater than the maximum speed, then we want to pass to normalize the velocity, and we do that by doing velocity equals velocity dot normalized multiplied by maximum speed. And now of course we need to change the velocity of a rigid body, and we need to pass the new velocity. Let's see what this will do. So if I go over here, I'm going to take my target and drop it, if Unity lets me of course, drop it to my script over here, and if I hit play, you will see, of course it needs to load first. You will see that we move towards the target. Now we move in the direction of the target, okay, but of course you see the spaceship does not rotate the way it should. So let's jump back into our script and let's add more stuff. Let's fix the rotation, and we need a new quaternion, the desired rotation, and this will be quaternion dot look rotation, and we will need to look towards the direction we are going. So we can do transform dot rotation equals quaternion dot slerp, a spherical linear interpolation, then transform dot, we pass the transform dot rotation. We want to lerp, spherical lerp, from our transform rotation to the desired rotation, and we want this all to happen by time dot delta time, and let's make it a little faster, so we multiply the time dot delta time to 3. We multiply it with 3. So let's go back once again into Unity. Let's hit play. Let me put this right in the corner over here. So you can see if I move around, my spaceship turns and rotates to the position it should. Now, of course, it's not ideal, and you can see it looks pretty much arcadey. So let's hit up the volume. Let's make it something like 50, and let's move him around. And of course, for higher volumes, higher speed, it looks more like it should be. Now, real spaceships, of course, have more stuff to do, and you actually in space you don't have friction. So if they are doing turns like that, they actually need to fire counter thrusters to stop moving from there, because there is no friction. They will be sliding towards the back. So now that we have our target, we can have our target over here. I'm going to show you now how we can do obstacle avoidance. Now we're going to use a lot of rays, and just so that we don't really need to, let me close the fixed update, start, let's include all this inside a region. Let's call these variables, just so that we are a little more organized. Oops. And it actually takes all the, let me see, so that we collapse all our variables and we have more room to move. So now let's create a function that will store all our arrays, so that we pass values and it will return us some raycasts, actually the hits of our raycasts. And I'm going to say raycast hit, this is going to be an array. I'm going to name it rays, and I want to say to use the direction, and I want to use an offset for the x, and this is a float actually. Now I'm going to use only an offset for the x. If you want, you can add offset y and z. Okay, I'm not going to use them over here, so I won't use it. So of course this needs to return a hit. Let's add it from here. Maybe let's just write it. So of course we need array, and that array will be a new array, and the new array we want it to be from our transform dot position plus a new vector 3, and that vector 3 will be the offset x 0 0 and the direction will be the direction we are passing to this function. Let's debug this just so that we know what is currently happening. Now, of course, the debug draw array needs a direction, but it doesn't take a distance, so for how much you want this array to be. So that way we pass the direction. Let's multiply it by 10 and multiply this by maximum speed, and we can actually pass a color. Let's a color with a capital C, and let's make it red. Now this is only for the debugger. Okay, no need to worry. Now we need float will be a distance to look ahead, so for how long the array is going to be, and I'm going to take my maximum speed and I'm going to multiply it by 10. So if we are going with 1/4, the array will be 10. Okay, you have to keep in mind that we move if you will move a lot faster, you actually have it's not that easy to turn and follow and change the direction you are heading. So you need to have room to know what is ahead of you. I'm simply doing it this way. You can actually do more stuff. You can multiply it by higher numbers, just so you want to know what will do, what your array is going to do. So anyway, let's move around. So we need raycast hit, and we're going to say hit or hits. So over here we need to say physics. Now you can do raycast all, but as you know, raycast is a simple line. We want to say an obstacle might not be something too small, and our spaceships are big objects. Okay, so let's make a sphere cast all and get a lot of the stuff that is in front of our spaceship. Now the radius, I'm just giving it a 5. Keep in mind that the 5 might be not work for you if you have different sized object, might be too big, might be too small. Okay, and the distance we want to keep doing the distance we want the array to have is the distance to look ahead. And since we have all this, let's return the hits. Okay, so now that we have our function for our arrays, let's add a new function, and this will be obstacle avoidance. We know we want to pass the direction, since we will be calling the arrays function from this one also. And we need an offset x. So the first thing we need to do is call our raise function. And this will return us everything we hit from the race. Now we should probably actually no, let's just start it from here. Okay, so let's make a for loop so that we can go through our hits. For integer I equals 0, I minus the hit dot length minus 1, I plus plus. And we say if hit. Now we're using a spherecast and the raycast tool because we have a lot of colliders inside our spaceship, and probably the first thing they are not in the same game object as we are, so this will probably be the first colliders we're probably going to hit are ours, so we need to make sure we're not hitting our colliders and take them as obstacles. So if the hit dot transform dot root dot game object is not equals with this dot game object, that means we are not hitting our own colliders, and we will say if we haven't saved the position, we need to store the target. We can make, actually let's make it into our variables. Let's add one more variable. Let's add it over here. We're going to say not tracked object, transform obstacle. So just so that we are saving the obstacle also, and we can have more control over it. So we store the target our player has signed, okay, or the current waypoint. Obstacle equals hit I dot transfer. Save position, we say true, otherwise it will simply every frame it will store a new position and nothing really will actually happen. Now we know that we hit something and something is ahead of us. Okay, so now we need to do something, since we know we have an obstacle to the front. And the way we do that is, let's make a void, let's make a new function. We will say find escape directions. We want to pass a collider, since that is what we hit, and we can pass the transform, but since more of the stuff we need to use are inside the collider and we don't want to keep and it's stored over here, so we don't want to call another gate component. Okay, now we're actually going to utilize raycast for every direction we can go. Since this is a spaceship, we can go up, down, left and right. If you want it to go diagonal, how do you call it? So anyway, if you want to go in an angle, you can say you can use more raycast over here. I'm just going to show you the main idea behind it. So for raycast hit up, we need to do the origin of the raycast will be the transform dot position of the collider, and of course we want to go transform dot up, and we want to pass the out hit up, and the distance we want him to go is actually we can take it from the bounds of the collider, the extent, and of course if we want to go up, the y. Now if we do this, we know that the position of the collider bounds extents.y is actually over here. Okay, but of course if we move our spaceship over here, it will actually collide with this. So one way we can clear this, we can multiply it by 2. So it's actually going to go double the position. So it will be around over here, somewhere like over there. But since our spaceship is big and we may be using these raycast to check from the wings, so we will add a new variable and a new float actually, and that float will store the current wingspan. Okay, from the one side, not the whole, but how much you need to go from over here. It's not really necessary to be exact. Okay, the way you can find it is put it over here and start moving a cube like this, and you can count. Now you don't actually have to be so precise, so get the exact wingspan. You can say, or maybe half wingspan. You can see how much of a clear you want to be. Now you can change all this according to what current state is the AI. So if you are if the AI is attacking, you can change this to be more close, and if it's not attacking, you can change it to have more room, something like that. I'm going to delete this cube, we don't need it. I'm going to jump back into my script. Let's add a new public float. Let's add it over here. Let's say wingspan. Now I've measured it, and about 12 is okay for my object, for my spaceship. So over here we simply multiply the 2 by the wingspan. Okay, so we're doing a raycast, but if we hit something with this raycast, so if there is something above above the obstacle, we don't actually want to do something. But if there is not something, so if this raycast didn't hit anything, then I want to save the direction. So the direction will be called transfer.position plus a new vector3 0 collider dot bounce dot extends dot y multiplied by 2, not multiplied by wingspan, by actually plus the wingspan. We don't want it to multiply it by the wingspan. If we multiply it by 12, it will actually go very far away, and that's not the thing we want to do. This needs the extends dot y, and where is it? Extend. Yes, it's how is it? Dot extends with a t. So if there is not an obstacle above our obstacle, then if our escape directions do not contain this direction, then what we simply need to do is add it. Escape directions dot add direction. Now let's copy all this and let's say hit down. Make sure you get and you change all this. Okay, so we covered the up, and now we need to do the opposite, which is not this, actually the transform.up. We need the negative of the transform.up, which is down. Okay, we need to also do over here. So the direction we want to check if it's saved is the transform.position plus new vector 3, the negative extent multiplied by 2 plus, not plus. If we do plus, we will be in the middle of our wingspan, in the middle of our obstacle, so minus the wingspan, so it's actually lower. Now of course we need to do 2 more times, and this will be hit.right, remove the minus, call transform.right, the direction we want to go. The out hit will restore our hit, will be hit right. Now we don't want to use the Y because obstacles might not be cubes, might be spheres, might be something else, and instead of the Y we will use the X, and all the other stuff will stay the same. Multiplied, the X will be multiplied by 2 plus the wingspan. And over here, instead of taking the Y, and this actually needs one more 0 and one more 0 and one more 0, since this is a vector 3 and we only had 2 floats. So for our right, we don't want to take the Y, so we will passing 0 to the Y, and to the X we will pass the collider.bounce.x multiplied by 2 plus the wingspan, and all the other stuff will stay the same. Let's copy paste that once again. Now you probably can store all this arraycast in another function and pass the direction you want to. You are currently doing, but anyway, let's just do it this way and be done with it. So for the final one will be the hit left, and we want the origin to be the transform of the collider we found, the other direction than the right, which is, it's the left, so minus call transform.right. We store it in the out hit left, and this will be the same. Now for the direction we need to do is, of course, the center of the collider plus new vector 3 minus the collider.bounce.extends.x multiplied by 2 and minus the wingspan. If it's going towards the center, then that means you did something wrong over here. You either add, or instead of subtracting in some way. So with this function we have all our directions. If you want to check for more directions, copy paste more and more and more. Okay, now of course these are 4 raycast, so you can optimize it a little bit. We're not going to do that over there. You can optimize it to happen if you don't want this raycast to happen every frame, since it's not every frame that you're probably going to find new obstacles. You can make it so that it happens only once per 60 frames, so it happens only if your game is running with 60 FPS. You can optimize it so that it only happens once per second. Okay, we're not going to show that. It's pretty simple. You can do it. I believe in you. So now we have over here in our obstacle avoidance, in our loop over here, if we hit something that it's not our own colliders, if we haven't saved a position, save that position. And now what is the next logical step is, of course, find the escape directions and the center from which the obstacle we need to find is the hit I.collider. So we need to escape from the collider we just found. And now that we have all our escape directions, let's do first a new function, and this will be the vector3 get closest. So this vector3 will check through our escape directions and will return the closest position we can go. So vector3 close equals escape directions 0. We need to do a check for the first distance so that we have something to compare it with. Transform dot position and with escape directions 0. Now for each, you can use a for loop. I'm just going to use a for each loop. So for each direction in escape directions, come on, so we need to check the temporary distance, and if this of course is vector3 dot distance with transform dot position the direction, and we will say if the temporary distance is minus than the distance. So if the temporary distance we are checking now is lower than the distance, then the new distance we want to be checking is this temporary distance, and the closest object will be the direction, and we need to return the closest vector. Now let's get this closed so that it gets out of the way. And now into our obstacle avoidance we will say if escape directions dot count is greater than 0, so if there are any escape directions and we haven't overridden the target we are currently moving, then something we forgot, the new target position which we haven't added. So let's add over here or over here vector3 new target position. So if we haven't overridden our target, And so where was it? Where was I? So we haven't overridden our target, then our new target position will be the closest. We want this to happen only once so that we are not checking every frame, which is the closest one. We want to have a check for the distance, vector3 dot distance, transfer dot position, and the target dot position. And then if distance is lower than let's say 20, but keep in mind that you have to take into account how large your spaceship is, and that 20 I will going to multiply that to add to that the wingspan of our spaceship. So if we reach that target and we have saved the position, then our target dot position will be the store target. So if we reach the new target, which is the target we want, we are going to avoid the obstacle we found ahead. If we reach that over there, then it means that we are clear, so return to the previous target. And we don't have saved the position anymore. Now override target will return to false, and escape directions, we want them to be cleared. Otherwise, the next time we'll be looking for escape directions, not actually looking, but looking through the list, we will have the previous entries, and it's going to make things pretty complicated. So that was the obstacle avoidance, and one of the last things we need to do is we need to go to our fixed update, and after we have our rotation, we have our velocity is actually called our obstacle avoidance function. Now we need the direction we want to do a raycast is forward, and we want this to happen from the center of our spaceship, so we'll pass the offset of 0. And over here I will say if we have override target, we will have a new target, so then the position of our target will be the new target position. Let's save and let's go back into Unity. So if I hit play, let's see what it will happen. Now let's visualize it a little more. The red is the raycast. This red ray is looking for obstacles. Okay, the white line is the direction of our target. So you only need to look for the red ray, and let's see what will happen when we find an obstacle ahead. And as you see, it found the obstacle and calculated. It did 4 raycasts to the right, to the right, to the left, to the up, and to the down, and found it that for all these directions, going down was the fastest one. But as you see here, it now bugs out because we have where was it? The distance is too great. So let's make it something small. Let's make it 5 plus the wingspan, or let's just simply do the wingspan without adding something more, and let's do it once again. So the error here was that we actually the distance we had to change the target was too small, so it took it that we are clear of the object, so it makes him turn the other way. Now, because we have the same values with where was it? With a move target, or pretty much the same, it's actually bugging that much. So let me see, where was it? So let's make it 10 minus lower than 10, and of course we need to have this. Let's make this also closer. We hit the ray, we are going towards our target, and when it's lower than 10 something, it's not. So let's see how we can debug this. And if you go to the icon next to the lock over here, you can change it from normal to debug. Now let's hit play and let's see what will happen. For now it works okay, but if it goes closer, it turns the other way, and we see that we're turning, even though we reach the target, we actually have the safe position is also true, and the override target is also true. So jumping back into our scripts, let's see what this distance has to say. Let's hit play. Let me stop that over here. You see the distance between this, the spaceship, and the target. We change the distance from this from the spaceship to this target, and let's see what will happen when we are lower than 25. So let's see, let's hit Ctrl F, let's hit 25, and here is the culprit. Okay, as I said before, because we are doing changes over here, we are checking if we reach the target, then we need to change how much close to the target we need to go. So let's go even lower, let's make it 5. And for our obstacle avoidance, not the direction, obstacle avoidance, over here, let me close that. The distance we need to say, let's say the wingspan. We know the wingspan is larger than 5 points, so let's hit play. We see an obstacle, see he is going to the target that is avoiding that obstacle, and when he reaches, he goes back to our target, the target. Now let's see what will happen if we added a new collider, a new obstacle to down of the other obstacle. Let's hit play, and as you see, he calculated that the upward direction is closer than the left or right. If we move this to the right, now keep in mind that if I had this over here, since we're doing a sphere cast, we might actually not hit it. Oh, because the raycast is larger, the sphere cast is larger, it can find it. But if we move it something like this, or if you have spaceships that are a little different sized, like from this one, might not really work. But since the wingspan is 12 points, it's actually a pretty big sphere cast. Okay, so there's no need to do additional rays. But if you had a spaceship that is something like this space station over here, let me resize that. Okay, you can do if you do a sphere cast that covers all this, which will probably be almost the whole level at this. It will be a pretty much way too big sphere cast. So if you want to be more precise, let me, oops, mayday. So let me get that out of the way. Let's go back to our gunship. So if you want, you can make more rays from each point of the wings, just so that you are sure that you are not hitting something with your wings. And the way you can do that is pretty simple, the way we wrote our script. And if I take my obstacle avoidance over here, copy paste it 2 times, and if I change the offset to, let's say, the wingspan and minus the wingspan, and I'm going to go back into Unity, and if I hit play, you can see that we are actually doing 3 rays. Now of course this is too much for the spaceship we are having over here, and as I said, you can optimize all this so that it happens every other second, not every frame. I'm going to delete those, and the final thing we need to do is where we are checking the distance over here. If we have saved the position, if we haven't saved the position, that means we reached a target. So if we had a list of targets, okay, I'm not going to write it, I'm going to show you how, but not really implement it. So if we had a list of an array of targets, or a list, whatever you want to use, and we have an integer that says that it's the index, or maybe let's say waypoints. So we have our waypoints. Then if we reach the target without having stored any other target, so we had we reached the waypoint we wanted to go, then you could simply say index plus plus. Okay, so it will change to the new target. So over where was it? Inside fixed update. So instead of using move towards target position, you could say move target waypoints index dot position. Okay, and when you reach the one waypoint without when we are at the waypoint we want, it will change to the other waypoint. Now, of course, this is a spaceship, so you can go around moving waypoints and making waypoints around the whole map. So you can simply randomize a little bit the direction, so you can make a new target to the front. You can change it to whatever you like and you want it to do, and depending on the current state the AI is, change it accordingly. So let's take our gunship a little back and let's create some more obstacles and see what happens. Let's see, let's make it over here and let's put a new target over here. Now I'm putting it into one direction since we only have one target, and if I put it over there it will simply just look towards there and go there. So let's hit play and let's see him find his way around. So he goes up, he will reach the first target, he moves the target around so that he can avoid obstacles, and he goes down. When he reaches the new waypoint, the new target, he will turn for his for the new position where he will avoid the obstacles, and when he goes to the new target, he will return to this target. Okay, and as you see, he was pretty close, so, and of course he reaches over here, so he doesn't know what to do, and it gives him the different direction. Or you can simply, if you want him to stop, you can go to move target and change this. If you multiply it by 0, it will stop. So let's pull him some limitations we have right now. Let's pull him back and let's turn into normal, and let's change the maximum speed to 50. You see that the array is depending on our speed to how much it's going to change. The distance is looking ahead. So if I hit now play, you see that the array is so much bigger, but that means that in order to go over here, it will actually need to have seen the obstacle further back. And of course, since the next obstacle is over here, it will be too soon, and actually he did a pretty good job at doing that. And of course, because he reached the target, he doesn't know what to do, but he takes obstacles and he moves around. Now the speed is moving, our spaceship is moving, of course. It has a lot to do with what current AI state the target is. So let's see some examples, or maybe let's see how we can change the speed around. So I'm going to add a new function. I'm going to say manage speed, and the maximum speed, so the speed we're currently having, is mathf dot move towards maximum speed. So the speed we're having over here, we want him to move towards the target speed, and all this to happen on time dot delta time. And let's make it happen a little faster, so we multiply it by 5. We need to drop this inside either fixed update or update. Since it doesn't have to do with physics, I'm going to make a void update and drop it over here. Now let's actually, outside of our region, let's make a new public enum, and let's say we need to add over here, and let's name it AI states. So what AI states we want to have? Let's say normal, let's say attacking, evade, and all that. So inside our update we can have, and actually we need to make a variable to store the enum, so we need a public, or actually this, let's leave it public. So public AI states, AI states, AI state. Yes, I wrote it wrong. So let's have a switch statement over here, and let's say AI state, and we will do checks for our cases, and the case for, and the first case will be AI states dot attacking. We need to add a break. AI states dot evade, case AI states dot normal, and I need to add a break under the evade, and I need to write the break correct, and we have all this. So we know the normal speed, what is going to be. So the target speed will be the stored maximum speed, or actually, instead of using store maximum speed, we can say public float normal speed, public float attacking speed, public float evading speed, and over here we pass the normal speed. The target speed will be the evade speed for the evading speed, and the attacking will be the attacking speed. Let's initialize them over here. Normal speed, what we have right now, let's have it 15. Attacking speed will probably be 60, and evading speed, we need to have a little more control, so let's say 25. Okay, so now of course you can do more checks. You can check if there are a lot of obstacles around. You can check a lot. You can make him match the speed of his target enemy. There are a lot of stuff you can do. I'm just going to show you how the basic idea behind it, and you can implement then your own logic and your own AI. So let's pull him, let's leave him, or let's pull him back, and the way we will see the changes in the speed is by changing the AI state. So if I hit play, you can see that he's trying to match the normal speed, which is 15. If I change this to attacking, he will try to match the attacking speed, which is 60, and as you can see that the array is getting bigger. And if I change this to evade, he will change his speed. Now of course it doesn't change his it doesn't clamp to a new position, but it happens over time. and it's more realistic that way. Okay, and if I change it to normal once again, it will return to the normal speed. So that was it for today. Now, if you want to have enemies and shooting like that, it's pretty simple actually. So I'm probably not going to show this into this tutorial. And if I move him around, you can see that he's actually turning around. So this tutorial is pretty much done. I might do some additional parts. We will see. And if you have any suggestions, of course, feel free to ask them. And I'll see what I can do. Either I'll answer you in a comment or make a video about it. Okay, so thanks for watching. Don't forget to like and subscribe. Don't forget to share with your friends if they want to be pilots also. So don't forget we have a Patreon page. You can support me if you want. You get, for just $5, you get access to a Google Drive where I have all the scripts from the videos, and you actually supporting us and a little community over here we have, so that we can have more free cool tutorials like this and we can be Star Lords ourselves. So thanks for watching, and I'll see you next time. Captain out.